works.
So let me start. Hello, everyone. First, I want to thank the organizers for such a interesting conference in such a special time, and for letting me speak in occasion like this. And I hope everyone is doing fine in this very special time. Today, I will talk about the collision in the interior of the wormhole. It's based on a paper I posted at the end of last week. So first, here's the outline of the talk. I will give some motivation, and I will very briefly introduce the main idea behind the talk. And then we will look at the one example in detail, the perturbed thermofield double, and we'll compare it with quantum circuit. Then it's the main part of the talk. It's about the collision in the interior of the wormhole. We will try to give a quantum circuit interpretation of that. At the end, I will point out various unanswered questions. So first, motivation. The wormhole, the Schwarzschild wormhole was interpreted as an entangled state. I mean, in short, ER equals EPR. If you trust this bulk geometry, then what it says that when Alice and Bob share the entangled state, if they send in signals, then the two infalling objects can actually meet in the interior. And also in the rest of the talk, whenever we have thermofield double, I will always assume that Alice holds the left side and Bob holds the right side, just for the convenience of the talk. But the fact that they can meet in the interior actually, I mean, this is a puzzling feature because there are no boundary interactions. Then how do they meet? I mean, when they meet, when they scatter, it's a how do we know how should this scattering happen? There are no boundary interactions, and this makes ER equals EPR a very mysterious statement. The goal of this talk is to give I will attempt a quantum circuit interpretation of this meeting. Roughly speaking, when Alice and Bob send in signals, they create growing perturbations in the quantum circuit. And the two perturbations can have overlap in the circuit. Can you see my cursor?
Yes.
Thanks. Let's say we have a quantum circuit with these lines represent qubits, these dots represent gate. Then you have some perturbation. I represent this in red. It grows towards the left. There's other perturbation that grows towards the right. In the circuit, there's some overlap. We will argue that this overlap represents the meeting of the two signals in the interior. So here's the main idea about the talk. If it's not clear for now, that's fine, because this is just a brief introduction. I'll come back to more details later. Let's first briefly review the main idea of bulk tensor network and quantum circuit. It was pointed out by various authors that the bulk geometry reflects the minimal circuit preparing the state. I took this picture from a paper by Lenny Susskind. Let's say on the left, we use this picture to represent a quantum circuit. Basically, this is thermofield double. We represent thermofield double by a couple of Bell pairs. All these black lines represent qubit, and time increases vertically. Both left time and right time increases vertically. As time increases, the quantum circuit is getting longer. So we basically model the dynamics here by a Hayden-Prescott type circuit. What we mean is that at each discrete time step, we randomly pair up these qubits, put them into pairs. And on each pair, we apply a randomly chosen 2-qubit gate. That's what this red lines represent. Each red line, each small segment of red lines represent a randomly chosen 2-qubit gate. And as time increases, the circuit is getting longer simply because we lay down more gates there. But from another point of view, if we somehow lay off this circuit horizontally, then one can see that it somehow corresponds to the wormhole geometry. As time increases, the quantum circuit is getting longer. As you go to later time, the wormhole is also getting longer. The lengthening of this wormhole somehow corresponds to the lengthening of this quantum circuit. Similar story works for pure state black holes. As we apply unitary time evolution to the quantum circuit, the state gets more complex, and the minimal circuit preparing the state gets longer. So the Einstein-Rosen bridge, let's say time increases here, the Einstein-Rosen bridge also gets longer. And also, the circuit time is dimensionless. And we somehow need some natural dimensionless time where we identify circuit time with a boundary time. That's the d tau is equal to 2 pi over beta dt, where dt is a boundary time, is a short time. Let's start from the simplest example, thermofield double, unperturbed thermofield double at t equals 0. We represent the thermofield double by S Bell pairs, where S the black hole entropy. And just S Bell pairs, that's the simplest circuit you can imagine. The corresponding wormhole geometry has minimal length. And also note that as we increase right time, the circuit gets longer towards the right. As we increase left time, the circuit gets longer towards the left. In this talk, left time always goes up, right time also goes up. Now we apply some time evolution. When we do time evolution, what we mean is that we apply all these gates here. Again, the gates are applied on, so we first pair up the qubits, and then on each pair you apply a randomly chosen 2-qubit gate. And these gates are represented by these orange dots. As you increase right time, you apply more gates from the right side, and the circuit gets longer in the right direction. And when you apply gates, when you increase left time, you apply gates from the left side. There is a crucial feature about these gates that I want to draw your attention. Later we will use this feature, is that when you have a Bell pairs like this, these orange gates can be undone from either side. Let's say we apply some gates from Alice's side, but then Bob can undo these gates. What does this mean? This means that these gates does not change the density matrix of row A or row B. They do not belong to subsystem A or B alone. It's like if I only have subsystem A, then when Bob applied these gates, it doesn't mean anything for Alice because Alice's density matrix doesn't change. These gates only make sense when you have the union of A and B together. Let's look at the corresponding wormhole geometry. The wormhole is getting longer, but notice that the part that's getting longer is outside A's entanglement wedge, and it's also outside B's entanglement wedge. The part that's getting longer is mostly, let's say, it's in the future of this RT surface. And this region, as we all know from the statement of ER equals CPR, only exists when you have both A and B. And this feature actually corresponds to the fact that these gates only make sense when you have both systems A and B. Next, we look at a slightly more complicated example. We perturb thermofield double at, say, time tw, left time tw, which is early time. And the geometry was studied by various authors. Roughly speaking, the crucial feature is that the horizon will jump out, and then there is the RT surface is still represented by the blue dot, and there is actual red region here. This red region is between the old horizon without the perturbation and the new horizon with the perturbation. This is a crucial feature, that the existence of this extra red region. we want to look at we want to study a circuit model that corresponds to this perturbed thermofield double. So here's the circuit model we will use. We call it epidemic model. Roughly speaking, we still represent the black hole by, say, S qubits, and in this picture, the black lines represent the qubits. And we represent the dynamics by a hidden Presco type circuit. At each, the time goes towards the left. At each discrete time step, we randomly pair them up into S/2 pairs, and on each pair, we apply a randomly chosen 2-qubit gate. Then how about the perturbation? We represent a perturbation as some extra qubit. I want to briefly comment that why do we consider an extra qubit here? Because we want to consider a perturbation that actually changes the density matrix. Once it changes density matrix, then the density matrix will no longer be exactly thermal. Its coarse-grained entropy will be larger than the thermal entropy. So we use this extra qubit to represent an increase of thermal entropy. Let's say we have an extra qubit that we imagine it carries some disease, and then any other qubit that has interact directly or indirectly with this qubit will get sick. I think everyone is very familiar with this model these days, and we call the size of the epidemic at a particular time as the number of infected qubit. Let's say at this time tau equals 2, the number of infected qubits is 1, 2, 3, 4. So here size is 4 here, size is 2 here, size is 1 here. And how does the size grow? As we all know these days, once you have epidemic, if you don't do anything, the size grows exponentially in time until saturation. So the rate of increase of a size, first of all, is proportional to the number of sick qubits. It's also proportional to the number of healthy qubits. So here is what you get, where we use the initial condition that the initial size is given by delta S. Delta S is the initial number of sick qubits. It's related to the increase of thermal entropy. I want to draw your attention that, let's say, in each time step, there are, if we pair them up into S/2 pairs, then actually there are S/2 gates are applied. But to simplify the algebra, let's count each gate as 2. So in each time step, S gates are applied. And among them, SEP, S sub EP of tau, this size, these gates involve those sick qubits. They can be undone by Alice, but they cannot be undone by Bob. Why? Because Bob doesn't have access to this extra qubit. And S minus SEP of a tau are the gates that are not affected by this extra guy. They are these orange gates. These gates can be undone by Alice as well as Bob. We will call them healthy gates. So if you count the total number of sick gates as well as the total number of healthy gates, this is a relation we will use later. The rate of increase of the number of sick gates at a particular time is equal to the size of this epidemic at this time. The rate of increase of the healthy gates means these orange gates, the gates that actually belongs to the union of A and B together. The healthy gates, rate of change of healthy gates is equal to the number of healthy qubits at this particular time. Once we have a model like this, let's compare this circuit model, this epidemic model with the black hole geometry. What one will see is that there is some match between the circuit in the geometry in the sense that there is a shared region between Alice and Bob. This region only makes sense when you have both Alice and Bob. And this somehow corresponds to this healthy gates that only make sense when you have both systems. And this extra region, which is inside Alice entanglement wedge, actually corresponds to this sick gates, these gates that can be undone by Alice but cannot be undone by Bob. In order to see this, let's do a very brief.
Ying, before you go on, there was a quick question from Edward. Could you remind us the significance of this extra red bit that comes into the circuit?
Good question. The reason I introduced this extra red bit is that I want to use the extra red bit to represent the increase of the entropy, increase of the thermal entropy.
Oh, okay, I misinterpreted. He's asking what's the significance of where it enters the circuit?
Oh, it's just the arbitrary time. It's like, okay, let's say I perturb this at time minus TW from left side. Then the minus time TW on the left side correspond to the circuit time, time TW on the left side correspond to a circuit time minus TW. Then you just imagine horizontally you have a circuit here, then it propagates towards the left. Okay. So the time it enters from the boundary is the time that the perturbation enters the circuit.
Okay, thank you.
Is this clear?
I think so, yes.
Okay, thank you. Let's do a brief calculation. Our goal is to compare this orange region with this orange gates and compare this red region with this red gates. We fix right time large, let's say at infinity, and we vary left time. We look at the geodesic here in BTZ geometry. The reason I took geodesic here is because in BTZ geometry, I can calculate the geodesic distance in detail. But in terms of time dependence, I expect that no matter you take action, geodesic, or the maximal volume slice, you'll basically get the same answer in terms of time dependence. So I draw the geodesic, and then I look at a portion of geodesic in the orange region, BC, and the portion of geodesic in the red region, AB. I look at how it depends on the left time. You will see that the time dependence here of d of AB dTL, the rate of change of this AB, is the same with the rate of change of the SiC gates in the epidemic model. The rate of change of BC in this orange part is the same as the rate of change of the healthy gates in the epidemic model. It's like the growth of this orange region corresponds to the growth of these healthy gates, and the growth of this red region corresponds to the growth of the sick gates in the epidemic model. I think in this particular calculation, we actually see perfect match, but I think this is simply an artifact of geodesic distance as well as the BTZ geometry. This is just toy model. There's no way to expect it's a perfect match. But what's crucial here is that they share the same key features: the growth of certain geometry and the growth of the size of operator. They share some key features, like initially there's exponential growth with exponent 2 pi over beta, and later there's saturation. They share the same features. That's why they have similar time dependence here. So what do we learn from this computation? What we learn from this computation is that, let's say, we send in this perturbation at time TW here. And then we increase the right time. We slice the geometry this way. When I increase the left time, it is as if I am scanning through the circuit towards the left. The same color, the slice with the same color correspond to each other. This slice, roughly speaking, you can say it corresponds to this slice in the circuit. The black slice corresponds to this slice in the circuit. This is another slice that corresponds to slice in the circuit. This is what we roughly learn here. We learned that the gates that can be undone by both Alice and Bob, the healthy gates are stored in this shared region, the region that only makes sense when you have both A and B. We also learned that the gates that can be undone only by Alice but not Bob, the sick gates, the red gates, are stored in a region which is inside Alice entanglement wedge. Are there any questions? Okay, now let's look at the same quantum circuit, but from point of view of Bob. First of all, without perturbation, what do we expect? Without perturbation, let's say Alice has done a lot of operations to make let's take left time to positive infinity. I mean, the circuit has grown very long towards the left. And then when we increase right time, what do we expect? When we decrease the right time, what do we expect? When we decrease the right time, Bob will just undo the gates stored in orange region. When I decrease right time, Bob will just undo the gates here. This is without perturbation. He will undo the gates here, stored here at a steady rate. But with perturbation, the story will be different. What do we expect? We expect that with perturbation, Bob, which holds the right-hand side, can undo these orange gates. But Bob should not be able to undo the red gates. So this feature must show up. Let's see how this feature shows up. This time we again look at the geodesic distance. We fix the left time at large positive infinity, and we vary the right time. What we will see is that as we decrease the right time, the rate of change of the part in the orange region, DAB, the rate of change here, is the same as the rate of change of the healthy gates. So the rate of change of this portion is the same as the rate of change of these healthy gates. So indeed, we see that Bob can undo these healthy gates, but Bob cannot undo this orange gate, cannot undo these red gates, these sick gates. So far, we only look at geodesic. Let's say if we take the point of view that the bulk due to a state at a particular time is the entire Wheeler-DeWitt patch, then we can actually say slightly more. Imagine that we are decreasing the right time. At each time step, S gates are applied. Some gates are cancelled by the gates stored here. Some gates are cancelled by the gates stored here. But what happens to the other gates? What happens to those gates that are not cancelled by gates stored here? They are stored in the past interior, actually. I don't have time to go over the mathematical details here. I will just draw a couple of pictures. So what will happen is, like, say, when you fix left time very large. Now when you have a right time very large, then this is roughly the quantum circuit. There is a perturbation comes in that grows towards the left. I draw them in red. And this orange region represents all these orange gates, which are healthy gates. And as you decrease right time, the gates will cancel the gates stored here, will cancel the gates stored in the future interior. And then when the time is between minus TW, minus T star, and minus TW, again, some of the gates will cancel the gates stored in orange region. But there is some gates that are not canceled. There will be an actual fold of gates here that are not canceled. And this actual fold of gates will be stored in the past interior. And when right time is less than minus TW minus T star, all the gates stored in the future interior has been canceled. And there's just the actual fold of gates here. And this actual fold of gates is responsible for the growth of past interior. First of all, I mean, the importance of this fold was pointed out to me by Wang Madasina. At first, I basically ignored this part. And I also understand that at this stage, I think this may not be too clear for most of you, but it doesn't really matter. It doesn't affect the later understanding. I mean, for those of you who get it, that's good. I just want to show you that there can be a detailed match between the quantum circuit and the change of geometry. But one thing, the punchline here is that I want to draw your attention is this time dependence, is that the DAB, the rate of change of DAB here, is the same as the rate of change of the healthy gates here. So what do we learn from all this discussion? What we learn from the discussion is this, is that as we decrease the right time here, it is as if we are scanning through the circuit from right to the left. These slices here somehow correspond to the healthy gates here. These slices here somehow correspond to the healthy gates here. And these slices here correspond to the healthy gates here. Once you have this, then it's very tempting to draw the conclusion that the trajectory of this infalling object in the interior close to the horizon somehow has to do with the perturbation here. Why? Because all these slices here, when I slice it here, these healthy gates represent the slice here. So it's tempting to draw the conclusion that this has to do with the part of trajectory that's close to the horizon. It's crucial that here our discussion are only sensitive to the part of trajectory close to the horizon. We didn't say anything about singularity. About this point, I think this is the most speculative part of the talk. About this point, I will just stop here. Later, it will use some basic idea, but it won't be too crucial. So this is the main part of the talk. It's about the collision in the interior. We will discuss the idea that the overlap of perturbations represent the meeting in the interior. Let's say if we trust this Penrose diagram, then we know that the infalling objects from the two boundaries can meet in the interior. Let's first imagine a situation where Alice sends something from the left boundary at TWL positive, and Bob sends something from right boundary at TWR positive. Then if you draw the quantum circuit, you see that there are actually no overlap. Positive time here, positive right time here, positive left time here. There are no overlaps in the quantum circuit. Correspondingly, the two perturbations do not collide in the interior. So far, we are only discussing neutral black hole. It's the two perturbations do not collide in the interior. But on the opposite direction, we consider what if, say, Alice sends something in at early enough time, negative time. Bob also sends something in at negative time. Then, if we look at the quantum circuit, there will be some overlap in the quantum circuit. So imagine you have some, say, quantum circuit made of these orange gates, and then a perturbation comes in here. It grows towards the left. Another perturbation comes in here. It grows towards the right. But there are part of circuit where both the red perturbation and the purple perturbation are present. The two perturbations will have overlap in the quantum circuit. And we want to say that this correspondingly, when you look at the Penrose diagram, the two perturbations will collide in the interior. This is the rough idea. Let's be more quantitative. I think there's a raised hand. Xiaoliang, how?
Sorry. Xiaoliang, can you unmute yourself?
Hi, can you hear me?
Yeah, I can hear you. Hi, Xiaoliang.
Hi, Ying. Yeah, especially in this overlap case.
Yes.
How do you know which perturbation goes which way? Because if I just draw a circuit, then I'm doing two perturbations which are affecting the whole circuit in the same way.
Good question. I think in this case, I am basically doing the most naive thing, that if I increase left time, I'm considering I look at the Penrose diagram as if I'm evolving upward in the Penrose diagram. I'm increasing left time as well as increasing right time. And I assume that when I increase the left time, the perturbation grows, the left perturbation grows towards the left. When I increase the right time, the right perturbations, the perturbations coming in from the right grows towards the right. But I think this is the most natural choice, and it works here. But when it comes to charged black hole, which I won't talk about today, which I still don't have a good understanding, then that there's some subtle features that comes in, as you pointed out, that as for in which direction
I
it
just
goes.
mean
But
like
here I'm
if
just taking
you,
the most natural choice, that one towards the left, one towards the right, depending on which one.
but I don't know how to make that a physical choice, because like if I imagine like I have a circuit and the perturbation is like I modify one of the tensors, or I add an extra gate to one of the qubits, then
Yeah, let's say we only have one perturbation, then I increase the left time.
If you have one perturbation, then if I think of physically, I'm doing some measurements to physical quantities in the rest of the network. I will see that both sides got affected.
But I only increase, let's say when I increase the left time.
I'm not sure how to.
Let's say the perturbation comes in from the left. When I increase the left time, I assume the perturbation grows towards the left. Isn't this a natural choice?
Well, in the picture you draw here, like if I have this perturbation at T, at WL and TWR,
yes.
So why the purple one only affects the right side rather than the left?
Because I am increasing the right time. Increasing the right time. It comes in towards the right and increasing the right time. I assume the circuit time corresponds to, so there's some circuit time, there's some correspondence between the circuit time and the boundary time. And when I increase the right boundary time, I'm increasing the circuit time towards the right.
That's true, yeah, that's true, yeah, but I don't see how that, like what I mean is if you have two perturbations, one is like the left one is even to the right side of the right perturbation, then
yeah.
Why isn't it just why shouldn't I interpret it as this one, the red one actually affects the right side and the purple one affects the left? I think there is an ambiguity. Yeah, I should let you continue, but no. I think if I literally just take the boundary system, the thermofield double, and then with these perturbations and translate that into a circuit, then I would have to like start with thermofield double, evolve time backwards, and then do it from there.
That's right. I think in order to fully answer your question, first of all, one need to, in my talk, I only say, imagine, let's say when I send in two perturbations, then I evolve the Penrose diagram upward. In order to fully answer your questions, first of all, one need to look at the past interior. And also, I believe new subtleties will happen for charged black hole, which I haven't fully understood yet.
Okay.
But I will first continue the talk. Thank you for the question. So once we have an overlap like this, one thing we can do is to that in this, how do we study this overlap region? We can estimate the number of healthy gates in the overlap region. Let's say imagine you have some circuit made of this, all made of these healthy gates, the orange gates, and there's a virus that comes in, the red epidemic, it grows towards the left, and the purple epidemic, it grows towards the right. Then in this overlap region, the probability of being healthy from the red epidemic is 1 minus the size of this red epidemic over S, the total number of qubits. It's basically 1 over the probability of being sick. And the probability of being healthy from the purple epidemic is 1 minus S of purple, SEP of purple over S. Then the probability of being healthy from both epidemic is a product of these two. So from this, then one can estimate the number of healthy gates here in the overlap region. And what we want to do is that we want to compare the number of healthy gates here with the spacetime volume of the post-collision region. Why do we do that? Because now recall that earlier I said that it's crucial to understand that there are kind of these healthy gates. They only make sense when you have both subsystems A and B. And in particular, how about the post-collision region? The post-collision region are shared between A and B. The post-collision region should store the healthy gates, if we trust early logic. From gravity point of view, let's look at the post-collision region. What will happen? This was studied in various early papers. What will happen is that in the post-collision region, a larger black hole will form, and the geometry mostly depend on a quantity we call delta T here, which is minus TWL minus TWR. Because of boost symmetry, the geometry only depends on this time difference. And a larger black hole will form. This RH is the horizon radius of the original black hole. This RH tilde is the horizon radius of this new larger black hole. In BTZ geometry, they satisfy a relation like this. And what I want to see is how this space-time volume of this post-collision region depends on this time delta t. Here's the, in BTZ geometry, here is the expression of the space-time volume of the post-collision region, where RH tilde is the new horizon radius in this region, and RC is the place where the collision happens. Again, because of the boosted symmetry here, RC only depends on delta t. Let's first look at early time, where delta t is much larger than thermal time, but much smaller than scrambling time. In this regime, the back reaction is very small. What do we expect? From the circuit analysis, we expect that the number of healthy gates in the overlap region grows with delta t. Why? Because as delta t grows, the number of the white region here, just when you draw a picture, you see that the white region here actually grows as delta increase. I need to explain this picture. I mean, I use this to represent a quantum circuit, and there is a red epidemic comes in, it propagates towards the left, and there's a purple epidemic comes in that it propagates towards the right. Let's estimate the number of healthy gates in the overlap region. I do an integral from this 2 times, and this is a d tau here. This is the probability of being healthy from the red epidemic. This is the probability of being healthy from the purple epidemic. This is some very simple algebra, and this is what you see. On the other hand, in this region, one can also look at the space-time volume of a post-collision region, and this is what we get. We see that these two basically exactly match up to a shift of delta t. And up to a shift of delta t by order thermal time. And note that delta t is the difference of these two. All these times are defined up to thermal time, because the perturbation we throw in have thermal energy, so all this time are defined up to thermal time. So the shift of delta t by thermal time is reasonable. And actually, in the question?
5 minutes.
Okay, thank you. And actually, in the earlier time regime, we can do something more. So far, we only look at the number of healthy gates in the overlap region, but we can look at the total number of healthy gates here. And we should say that the total number of healthy gates somehow should be stored in this entire orange region, in this shared region. And indeed, that's what we find. Here's the, if we change the integral time from minus infinity to plus infinity, this gives the total number of healthy gates. And one can compute the space-time volume of this region. It's a sum of a bunch of pieces. At the end, this is what you get. Next, intermediate time regime, where delta t is larger than t star but less than 2t star. There will be some back reaction. The back reaction is not significant yet. From the point of view of quantum circuit, you will see that now the number of healthy gates starts to decrease as a function of delta t. And indeed, this is what you found. From the point of view of a gravity picture, this is what you get. You see that they again match up to basically the same shift of delta t. Now, late time, when there will be significant back reaction here. First of all, when delta t is much larger than 2t star, from the quantum circuit, you basically expect there are no more healthy gates. Because when this epidemic grows towards reaches the largest size, this epidemic also reaches the largest size. There basically will be no more healthy gates. Indeed, one finds that a healthy gate basically is exponentially small. And this is what we find. space-time volume of the post-collision region. In this case, they don't exactly match, but they have the same key feature in the sense that they both decrease exponentially in 2 pi over beta times delta t minus 2t star. Here is the full comparison here. Let's say I take t star equal to 36, not too large. I mean, if I take if I take t star much larger, the picture will be much prettier, but somehow Mathematica is doing something funny when I take t star too large. The blue line here gives the volume of post-collision region as a function of delta t. The orange line here gives the number of healthy gates as a function of delta t. One see that up to a shift of order 1, they basically match exactly. And here I take the derivative of these two. Again, in this entire range, one see an exact match. They deviate from each other when the time is close to 0 and when the time is close to 2t star. I mean, one do not expect they match exactly. After all, epidemic model is only a toy model. And to some extent, the space-time volume is just an arbitrary choice. I chose this choice because this is easy to compute. But one expects that various quantities, you take action, you take geodesic distance, you take volume of a spatial slice, they have the same key features of time dependence. But the exact details, we really don't expect them to match. One can look at a more detailed comparison of time dependence here. So let's do this. We increase the write time and see how the post-collision region, the volume of post-collision region grows as a function of write time. The rate of increase of the volume here is given in this blue line. And on the other hand, from the quantum circuit analysis, we also look at how the number of healthy gates, the orange region here, grows as a function of write time. We draw it here in this orange line. We see that these two lines also match well. This basically explains why earlier we find a good match of the total space-time volume post-collision region and the total volume of this, the total number of the healthy gates here, because the total volume of a post-collision region is the integral of this blue line here is the integral of this. The total volume, the total number of healthy gates is the integral of this. I mean, we see a more detailed match here. And this is my last slide about some, I want to point out some unanswered questions. First, this is very closely related to what Xiaoliang just asked. It's about which direction things propagate. I mean, so far our story only works for neutral black hole. For charged black hole, when you send in two signals, no matter how late you send in the two signals, even if you send two signals at large positive time, they will still meet. And how to explain this? I don't know. I believe the answer will involve what Xiaoliang just mentioned. It's about in which direction the signals propagate. And another immediate question is how to diagnose if two perturbations overlap or not. We say that, we claim that when the two perturbations overlap, there will be collision. When they don't overlap, there's no collision, but how to diagnose this? This idea of overlap or no overlap very much smells like some kind of commutator. However, the most naive commutator, left and right, you always get 0. That's a big problem. And also, our story didn't say anything about singularity. So far, our story is only sensitive to the trajectories of this object close to the horizon. I mean, if we're really naive, we would just follow our nose and try to extend our story, then it feels like when things get to the singularity, the perturbation is supposed to get simple. But since our story doesn't work for charged black holes, so this is far from conclusive. I mean, the singularity remains a big mystery. Thank you.
Okay, we can all thank Ying for her interesting talk, and we have time for a few questions. If people want to raise their hand, I can unmute the. Okay. Taco Mori, can you unmute yourself?
Yes. Can you hear me?
Yes. Go ahead.
Okay. So, are you considering time-independent perturbation here?
Sorry, say it again.
Are you considering time-independent perturbation here? I mean the what kind of perturbation are you
Oh,
considering?
it's a time-dependent perturbation. It's you throw in something, then you forget about it. I'm not considering the relevant perturbation of the theory. It's just you evolve it with normal Hamiltonian. At some point, you change a Hamiltonian, and then you forget about it. Just throw in something. That's it.
And so it doesn't depend on the strength of perturbation we consider.
Doesn't depend on what?
I mean for example, like you can consider a situation like quantum quench as well.
Oh, I see. This isn't a quantum crunch situation because for the quantum crunch situation, you change a Hamiltonian, then you no longer change back. Here, I just locally perturb the Hamiltonian by throwing something.
I see.
Sorry, I should have clarified this before. Thanks for the question.
Let's move to the next question. We're back. Xia Wang, can you unmute yourself?
So sorry, I missed one simple thing. So the volume after the collision.
Yeah.
What's the definition of that?
The post collision. Sorry, I should have explained that. It's just can you see me? You imagine you have one shockwave here, one shock. Let me.
Yeah.
See. The post-collision region is the region is a region after the two perturbations.
Right.
Is
And
this region?
volume?
Can you see my cursor? Is this region?
Yeah. But when you call volume, you mean?
I compute the space-time volume, but the quantity.
Space-time volume. Oh.
But the quantity to use actually doesn't matter. When I first started working on this, the first thing I look at is really naive. The first thing I look at is the geodesic distance here between the two points. Because I was working in BTZ geometry, this is actually not singular, and they have the same time dependence.
I see.
The reason I didn't use geodesic or space-time volume or spatial volume is because I couldn't compute them exactly in this case.
And so let's say if I fix the time and then I'm increasing the strength of the perturbation.
Increase the strength of perturbation. Yes.
It's like if I make it stronger, then this volume will shrink.
Yeah, the volume will change. Notice that in my answer, there is a parameter delta S1, delta S2. Delta S1 is the increase of thermal entropy from this one. Delta S2 is the increase of thermal entropy from this one. When I match them, I consider that both delta S1 and delta S2 appears here.
I see.
This controls the strength of the perturbation.
I see. And the interpretation is that when you, I mean, naively I would have thought the number of gates infected will be the same.
The number of gates infected, the scrambling time will be slightly different. That's the difference.
Oh, I see.
When the perturbation is larger, it takes less time to scramble. It's like in epidemic model, the initial size will be different. Imagine an extreme situation if the initial size is the same as the maximal size, then you basically don't have healthy gates, so it will affect the number of healthy gates.
I'm going to suggest we move to the next question. If Xiaolang, if it's still not clear, maybe you can continue in the Slack channel. There's an opportunity to have longer discussions there.
Yeah.
So I'm going to ask Ping Gao, can you
Yeah.
Sorry, can you? Okay.
Okay, yeah, thank you for this talk. I have basically two questions. The first is that in your cartoon, you have the red and the purple like disease seeds on
Yes.
different qubit. But what if they can be the same qubit, or in along the evolution, could they get overlap, like in fact the same qubits?
Good question. Good question. I think I'm not really sure. I think they can. There's one conclusion I didn't I didn't talk about in the talk, is that one can naively just estimate the number of the qubits that get sick from both of them. Just follow the cartoon model, and the ratio of these doubly sick qubits with the number of healthy qubits is proportional to the collision energy. But since I don't understand the reason, so I didn't explain it.
Oh, I see. Oh, I see. But from the probabilities point of view, it seems like this will also change your epidemic like a growing rate, right? Because you consider like overlap of two. I think
Yeah, but when I consider the number of healthy gates, I'm taking the most naive approach. It's just the probability is being healthy from the first one times the probability of being healthy from the second one.
Yes.
This will not change.
Oh yeah, okay, I see. Okay, my second question is like any left perturbation from the BTZ from the thermofield double were understood as the right the perturbation from the other side. How could we see this feature in your quantum circuit? For example, a perturbation in the left after like a sandwich with the E2 beta H over 2 will become a perturbation from the other side.
Yeah, I mean, from this, I would say that they share the same circuit. It's like when I increase right time, it's as if I'm decreasing the left time. It's like they share the same circuit. That's how they see each other. Hello, does this help?
He says okay. So let's thank Ying again for her interesting talk. And I'll repeat, if there are more questions that people would like to follow up with, there's an opportunity to do so. There'll be a Slack channel set up specifically for Ying's talk. So thank you again, Ying. And now we